Use the integral test to determine whether the following series converges or diverges. So we are adding up the sequence n over e to the n. Alright, so what shall we do here? Okay, so n equals 1 up to infinity, n over e to the n. Now we need to use the integral test. So before we do, we've got to make sure our conditions are satisfied for n greater than or equal to 1. And if they're not, we might need to adjust and look at a tail of this particular series. Okay? So what do we need to show? We need to show that this particular sequence is decreasing, or rather, because the integral text talks about a function, so we just replace all the n's with x's. That's the most logical function to use. We need to show that this function is decreasing, at least eventually. We need to show that it's positive. That's not going to be hard to deal with. And that it is continuous. Okay. Now, e to the x is never going to be 0, so x over e to the x, always defined. Division of two continuous functions is continuous, so there we go. That one's not hard to show. Okay. Positive, well, e to the x is always positive. And for x greater than or equal to 1, that's positive. Positive over positive is positive. Now, how about decreasing? Okay. Is this decreasing for x greater than or equal to 1? Well, the easiest way to deal with that is to take the derivative. So we use a quotient rule, or I suppose you could rewrite it as x e to the minus x. In fact, that might help us when we do our improper integral, because then we might use something like integration by parts. Alright, so you'll have x, and then the minus sign comes down, and then plus e to the minus x, so that's going to be 1 minus x e to the minus x. Alright, so this is, so e to the minus x is always positive, so this is negative when 1 minus x is negative. And so that happens for values of x that are greater than 1. Okay, so we really have a choice. What happens sort of for this function, what we're seeing here, is that it's going to have a derivative that is equal to 0. So it sort of peaks right at 1 and then starts decreasing. Okay, that's what we're seeing here. So depending on how much of a stickler we are for the rules and the inequality signs, we might then say, okay, this holds for greater than or equal to 2. Let's look at a tail. Because if the tail converges, or if the tail diverges, then the series converges or diverges. Okay, but you know, we're decreasing. Okay, we're not actually ever increasing. There's no point past our starting point 1 where the function is bigger than it was a moment ago to the left. So I think the integral test is satisfied, but if you want to work with the tail, you go right ahead. Okay, so what does that mean? Well, that shifts now the question to this type 1 improper integral. Does it converge? Does it diverge? Okay. So we're going to have to swap it out for a definite integral, because definite integrals we can use the fundamental theorem of calculus on. And then we can find antiderivatives and plug in 1 and d. Speaking of which, what does an antiderivative for this look like? Usually we get something simple, don't we? And so we can just plug it in right away. But here we're going to have to use integration by parts. Okay? So I'll let my dv be e to the minus x dx. I'll let my u be x. So we'll get u e to the minus x over negative 1 minus, and then our du is just dx, and our v is e to the minus x over minus 1. Let's simplify these minus 1s here. Put a minus here, put a plus here. Okay, but this I know how to integrate. Okay, just e to the minus x over negative 1. which again we can simplify and just say minus. Okay. So we can get minus 1 minus x e to the minus x. So that's what the antiderivatives look like. You could use a plus c, but since we're about to put it into a definite integral, it doesn't really matter for us. Okay, so that was all just a little detour. So now our limit becomes evaluating minus x from minus 1 e to the minus x 1 to b. Okay. So we'll get minus 1 minus b over e to the b. I'm choosing to write it this way so I can L'Hopital's rule in a moment. Okay. And then minus, then we plug in 1. So minus 1 minus b over e to the b plus 2 over e. Okay, now we don't really care about this. We wonder, does this part converge? So let's just look at that. I'm even going to bring a minus sign out and change it to b plus 1 over e to the b. Now as b tends to infinity, the top goes to infinity, but so does the bottom. And if you're comfortable with limits, you might just say, well, exponentials always grow faster than polynomials, so this is going to go to 0. Or you could say, well, let's just use L'Hopital's rule, shall we? Okay, so still keeping this minus sign over here. Derive the top, derive the bottom, and then, oh, look at that, it does go to 0. So technically it's minus 0, but still 0. Okay, so the limit exists. In fact, quite specifically, this limit is just 2 over e. Okay. So the type 1 integral converges, and what does the integral test say? Well, the integral test says our series will do whatever the type 1 improper integral does. So we can say by the integral test, okay, n over e to the n converges. Well, there we go.